Okay, we're going to construct a trapezoidal approximation graph for the function y equals 3 plus x squared on the interval, x interval from 0 to 2 by increment 0.5. Now, might be clear to you what I mean by increment 0.5, but let's be sure we understand this. Our x values then are going to be, well, x is going to start at 0, and it's going to proceed to 2 by increments of 0.5, which means the next value will be 0.5, then 1, then 1.5, then 2. Now, to get y values, we plug in these x values. Okay, when x is 0, y is obviously 3. When x is 0.5, excuse me, 0.5 squared is 0.25, 1/2 squared is 1/4, so our y value will be 3.25. When x is 1, x squared is 1, so y is 4. The square of 1.5 is 2.25, added to 3 gives us 5.25, and 2 squared is 4, which added to 3 gives us 7. So, using these values, we can construct our trapezoidal approximation graph. I start with an x-axis where I've labeled the points 0 through 2 by increment of 0.5. Then my graph altitudes are going to be the y values. Okay, so we have a y value of 3 starting here, then a little bigger than 3, 3.25 here, and then we move on. I'm going to label these off camera, but you ought to see yourself, you ought to sketch the graph yourself and see if you come up with the same thing I do. Okay, so I've completed the sketch of the graph altitudes, and I'll draw the approximating segments. More or less straight. That one had a little dip in it, but we understand these are supposed to represent straight line segments. And of course the curve for this graph is going to be concave upwards, and the curve will dip a little bit below each of these straight line segments. So the actual curve is a little bit below the curve, or the trapezoidal approximation. Now I've made a table, x values, y values, same numbers that I had up here, and the table's a convenient way to organize our calculations. We need to calculate slopes and areas, and then accumulated areas. So, to calculate our slopes, we need to calculate rise and run. And then we can divide the two to get our slope. And then we need to calculate the average graph altitude. And I'll include width, although that's going to be the same as our run. And then we get area, and finally accumulated area. So we can fill these quantities in. From 3 to 3.25, the rise is 0.25. Now it should be clear that the width of every trapezoid is going to be 0.5, and I'll kind of indicate the widths here in blue and indicate these are the widths. And of course, the run is in each case going to be equal to the width. That's going to be 0.5. The slope of our first trapezoid then is going to be rise divided by run, 0.25 divided by 0.5, which is 0.5. Okay, the average altitude. Well, the average altitude's average between the 3 and the 3.25. That's going to be 3.125, and you should be able to do that in your head. You shouldn't have to reach for a calculator to do that. Width is 0.5, So the area is 0.5 times 3.125. Now, 5 times 3 is 15. And 0.5 times 0.125 is half of 0.125, which would be 0.0625. I'll write that as 0.06, assuming we don't need a huge amount of a huge number of significant figures here, but we could have written the exact result here. Since these figures don't represent anything that would limit the number of significant figures, it wouldn't be inappropriate to include all the significant figures. Now, if these are observations of some quantities, as they wouldn't be if you had a function, then it might be appropriate to include all the significant figures. And in fact, that wouldn't be a bad idea here. But I'm going to keep things to just a couple of decimal places in most cases. The accumulated area then is 15.06. And of course, you probably already recognize my error here. If you don't, see if you can't spot it before I correct it. Okay, I got carried away with getting the numbers right and didn't think about my decimal point until I got over here and realized that area 15 was not appropriate to these numbers. When I wrote that down, I realized it. And I went ahead and did all the significant figures here, although I probably won't do that all the way through. Okay, so right here are the numbers for our first trapezoid. Now I'm going to go ahead and write those in as best I can, because I don't have a whole lot of room here in this first trapezoid, but why don't you go ahead and try to figure out the rest of these numbers. Okay, I've calculated the second row here, which would correspond to the slope and area of the second trapezoid, as well as its accumulated area. You might have also noticed I got rid of a 0 between the 5 and the 6 there. Didn't belong there. It came out of the recesses of my imagination or something, but the significant figures didn't match up with these, right? So I rethought that. Probably should have grabbed a calculator, don't you think? Okay. And of course I'm going to label those, and then I'm going to fill in the remaining columns. Okay, the rest of the table has been filled in. I'll comment again, that might be a ridiculous number of significant figures, and of course our graph can't represent even a third significant figure on most of these quantities. And I've been inconsistent on the graph. Here I have labeled 3.375, just because that's a pretty familiar fraction, 3 3/8. But I've just labeled the 1.81 up here, the 2.31. So I've not been consistent. I've used 3 significant figures everywhere but here. Again, I couldn't resist the temptation to use an exact fraction that everybody should know. That 0.375 is 3/8, indicating that most of these are going to reduce to pretty simple fractions, and we could have done these in fractions and obtained perfectly sensible results. Okay, well, regardless, the numbers here match the numbers up here, and the numbers here I believe have been calculated correctly, and there's probably no real discrepancy. So you should double check me, make sure it's right if you haven't done so already. But right there's our graph. And for easy reference, right here's a table indicating the numbers on our graph. Sometimes it's easier, once you understand what the numbers in the tables mean in terms of the graph, to go ahead and just read those numbers. Okay, so I've circled the essential columns, the y values, the values of our function, in other words, our slopes, our areas, and our accumulated areas. And this information is ripe for interpretation. If we happen to have some kind of real-world interpretation for this function, then, for example, if this is velocity and this is time, then we know how to interpret the slopes, the areas, the accumulated areas. Okay, if it's pay rate versus time, similarly. If it's value of investment versus time, force versus position, position versus time, whatever it is, we're ready to obtain information about that system. If it's just of theoretical mathematical interest, what's the exact area under this curve? Well, it's not going to be exactly the same as the area under this broken line graph, but it should be very close, because if you take into account the curvature, there probably isn't but maybe a 1 or 2% difference between the area under the smooth curve and the area under these segments.